Okay, so the thing about this question is that we have to understand, we have to be able to use the concept of what a between statement actually says to us. Okay, and that's what this is. So 7 is less than or equal to x, absolute value of x less than or equal to 9. If this is a between statement, there are really two inequalities there, right? Okay, we talk about this being a compound inequality. What we need to be able to realize here is that this thing, if ever you have, I'm just going to use, like if A is less than X is less than B, okay, if that's occurring, then you get two things. You get A is less than X, and X is less than B, right? That's what you get from that, okay? Now, we've talked how it's easier just to say that A is less than X is less than B, but those two things are congruent statements, okay? Now, if I've got absolute value in that middle term, okay, I have to be able to apply a between statement like this here, okay? Meaning that we have to be able to break this down into 7 is less than or equal to the absolute value of X, and the absolute value of X is less than or equal to 9. Okay? So there are times, and this is really the only time that I can think of right now that we actually need a good understanding of a between statement, meaning that it's an and statement and you can pull it apart this way. Okay? You have to do it this way with absolute value because now think about what it does. That itself gave you two statements. However, when I rewrite this as absolute value of X is greater than or equal to 7, doesn't that give you two statements as well? Because remember, we had the absolute value of AX plus B is greater than C, then you get AX plus B is greater than C, or AX plus B is less than negative C. That was our rule that we talked about with greater than absolute values, right? So this is going to break down to X is greater than or equal to 7, or X is less than or equal to negative 7. Does that make sense, everybody?
Yeah.
Okay. The one thing I got to caution you on is at that stage right there, people see, they read that at 7 is less than X, or absolute value of X. And they think, oh, it's less than, so I'm going to rewrite this as a between statement. It's less than in that order. In order to be able to apply our if-then statement. If you guys remember back to the law of detachment in geometry, the only time that I can use this if-then statement is if what I'm looking at, my particular problem, my scenario, matches to the hypothesis or the if statement. Okay? So right now, if I look at 7 is less than or equal to absolute value of X, that is not matching what I highlighted there in blue on the right. Okay? It's not until I use a symmetric property and flip that inequality around, and now I have the absolute value is greater than or equal to 7. Now you match the hypothesis. Now the law of detachment says you can then make the conclusion of X is greater than or equal to 7 or X is less than or equal to negative 7. Does that make sense? Okay? That idea, that's why, and I talk about this because we're doing it right now in my geometry class, but that, if you remember back 2 years ago, about this time, we spent an immense amount of time talking about if-then statements and how algebraic rules, how geometric rules, all of our rules mathematically are presented as if-then statements, okay? Because it tells you how to apply rules, okay? And then we talk about if and only if statements where you can apply it kind of two different ways. But I think that's an important thing for us to talk about because if you understand that, okay, and I'm going to be honest with you, I didn't really fully understand that when I was your age, okay? But once I did make sense of that, and I could realize what my rules were and remember them, okay, or develop relationships to help me remember them, math became so much easier, okay? Because it then essentially tells you what you need to be doing. So now in this one, I got x is less than or equal to 9. Well, less than or equal to 9, that's the rule that says if absolute value of ax plus b is less than c, then you can write it this way. X plus b less than c. You can write it as a between statement, or if you prefer, if you want to keep using an and statement and kind of segment it that way, you can. I'm just going to rewrite this as negative 9 is less than or equal to x and less than or equal to 9. Okay? So if we think about that absolute value of x is greater than or equal to 7 produces two individual inequalities, right? The absolute value of x is less than or equal to 9 produces two more individual inequalities. What was the key word that was keeping these two together? And. So we kind of got like maybe kind of an order of operation type thing going on here with these structures. I have this is produced from this left inequality. This is produced from the right one. They need to be attached with the word and because that's the way it was at the beginning. Okay? Now, remember, and means intersection, right? So it's going to be hard for you to visualize what your answers are here without drawing a graph. My suggestion is the more complex your results look, the more inequalities that you get, the easier it will be to decipher what your answer is with a graph. Okay? So it's not a hard thing to sketch out. So she'll make my number line. The only values on here that we need are 7, negative 7, 9, and negative 9. So put those on. Okay. Now this red one, the red one says x is greater than or equal to 7, right? Greater than or equal to 7 would be that stuff there, right? So we got that one. This one says less than or equal to negative 7. Would be that one there. Is that doable? So we've taken care of that. Now I'm going to do the black one. Negative 9 is less than or equal to x is less than or equal to 9. My hopes are that we all feel comfortable with graphing that, finding our endpoints of 9 and negative 9. Then x has to be between, right? So that's that. All right, so we graph the individual parts, the parts that I've got parentheses around, we've graphed those individually, right? Now, what's the word that merges those? Or connects and, right? And means what to us? Graphically, it's the intersection. I heard somebody say intersection, okay? So we look for the intersection. So if I look for the intersection, don't they start intersecting at 9, negative 9? Yeah. And go up to 7, or sorry, negative 7? Yeah. Are they intersecting here? No. Are they intersecting at 7? Yeah. Up to positive 9? Okay, so the way we answer this then, left to right, is negative 9 included, up to negative 7 included. We skip some values. We'll get back up to 7 included, finish at 9 included, and we union those two. So that's kind of what we're looking for on questions that incorporate an absolute value in a between statement. Okay? Now, this was a very kind of elementary type between statement because that expression was very simple, right? Basically, when we apply the absolute value rules, there's no algebra to do after that, okay? But if that was like an x plus 2, an x minus 3, a 2x plus 5, whatever expression you want it to be, you would then, at those individual stages, right here where I've got the parentheses and here I got those parentheses, you would actually do then that further algebra to isolate your x, right? But I think that's something that comes without saying, something we can do without having to see an example of that. Is that all right with everyone on that one? So then I think the next question, that was like, not sure what number it was, towards the end, maybe like 18-ish, maybe beyond that. This is the next one right after that, okay? So this is the same idea, right? The only thing here is that this is almost kind of a special case, and it's a special case because of that zero. But this is the approach that you would take, regardless of whether it being a zero or not, okay? Between statement tells us we get two things. We get that one there. So 0 is less than the absolute value of x minus 5. And then we get that one there, right? Absolute value of x minus 5 is less than or equal to 1/7. So that's just breaking it apart. That's saying what that original problem says in an alternative way, a way that we can actually manipulate things. I don't like the way I've got that written in red, so I'm going to use the symmetric property and just flip it. Remember, when I do that, the inequality sign still needs to be, I like to think about that inequality sign as kind of being like the head of an arrow, and whatever it's pointing to in the first line, pointing to the 0, it needs to be pointing towards the 0 in the second line when I flip things. Just be careful with that. So now, this turns into an OR statement, doesn't it? So we get x minus 5 is greater than 0, or x minus 5 is less than, now you negate 0, but it just gives you 0 again, right? Yeah. And that's kind of the special case. That it's kind of a weird thing to do. People, I'm doing something wrong here because 0 can't be negative. Well, you can multiply by -1. It doesn't do anything to it, okay? But we need that second one here, okay? Because if you think about, this is saying x has got to be to the right of 5. This is saying x has got to be to the left of 5. If we don't have this one, we get ourselves in a little bit of trouble with this problem. So I'll go ahead and finish this. X is greater than 5, or x is less than 5. Okay? And then we'll come over into the blue one. The blue one, that is a less than, so that's going to give you negative 1/7 is less than or equal to x minus, can I write this as 35/7 is less than or equal to 1/7. You just want to be able to add fractions, right? Add and subtract them. So add 35/7 to all three parts. So it's going to give me 36/7 over here. And over here it's going to give me 34/7, right? For what? All right, so we got and here, right? So if I graph this, and remember this and came from that and right there. That has to stay throughout the problem. If I graph the red one, okay, I'm going to find 5. And the red one says that we got to be greater than 5, or x is less than 5, right? So that's every single number on my number line except for 5, okay? Now the blue one, I'm looking for 36/7 and 34/7, so those are just to the right of 5 and just to the left of 5. And what that's saying is that we're going to have x values between those two things, right? Okay, everybody? So now because of the word and. So those are the individual absolute values. Okay? The word and says now we're looking for the overlap, right? Do you guys agree they start overlapping there? And they go up to what number? 5. They stop overlapping at 5, right? But then they jump over 5 and start overlapping again until 36 sevenths, correct? So the way we want to write that is we started at 34 sevenths. They both had that on their graph. 34 sevenths was shared. We get up to 4.999999999999999 as many times as you say it, right? Well, I can't write that, so I write it that way. And that indicates that 4.9 repeating number. We're going to jump over 5. We're going to jump over 5. Don't wake yourself up. We're going to jump over 5.
What? What's that one? I look up there and you're like, I'm not at all. Say that random part.
So we jump over 5. We have a brawl in here. We jump over 5, and we go to 36 sevenths, and we close off 36 sevenths.
Why is it undo and not like the
Intersection?
Okay, so that's a good question. So the intersection that you're wanting to put there is what we use to get this green stuff, your overlap. So we're saying that this interval here and that interval there, those are the only two things that are solutions. So we got to say all of these are solutions along with all of these. So that's why we use the U. Never. Because if you use the other one in a interval notation, there is going to be a better way of writing it. You can write it as a more condensed statement. Meaning if I had something like if you wrote, let's say, 2 to 6, and we intersect 4 to 8. The 2 to 6 would be that, right? The 4 to 8 would be that. And this means intersect. This means the overlap, right? So isn't the overlap then between 4 and 6? So that's what we would write instead of saying that. Does that make sense? Okay, so we'll get to this last. Does that help on those types of questions? Okay. Now this last one says solve the inequality, and this is the last one on the assignment. We see that inequality, so that absolute value in the bottom, and we just shut down. Okay. It's just a number, is it not? Absolute value of 2x minus 9 is just a number, so it's like maybe it's 12. Okay. Well, if I was 12, wouldn't I multiply both sides by 12?
Yeah.
Okay. If it was 30, wouldn't I multiply both sides by 30?
Yeah.
So what are we going to multiply both sides by here? Absolute value of 2x minus 9. So I'm going to get 1 less than or equal to 5 times absolute value of 2x minus 9. Now, before I apply my rule, I'm going to flip this around, and I'm going to divide both sides by 5. So I should get something like that, right? 2x minus 9 is greater than or equal to 1/5. Okay, when I do that, my inequality is still pointing to the 1/5 side or the 1 side. If I did it before I divided. So now this is an OR statement. So we should end up with 2x minus 9 is greater than 1/5, or 2x minus 9 less than or equal to negative 1/5. It's 45/5, so I get 2x is greater than or equal to 46/5. Okay. What are you going to do next in that? No, you're not. You're going to multiply by half. Because you're going to think ahead, right? Think ahead. You got fraction there. I don't want to divide 46 over 5 by 2. I would rather take 46 over 5 and multiply by half because it's the same thing. Okay? It's just quicker if I multiply by half, right? So I don't want you to do a calculator because a lot of people will do this. 46 divided by 5 divided by 2. And it ain't going to be right. Okay? So let's go 1/2, multiply by 1/2, so it gives me 46 over 10. And 46 over 10 is 23/5, right? Okay. So x is greater than or equal to 23/5. Here, I'm going to get 2x less than or equal to 44/5. And then x will be less than or equal to 22/5 once I'm done multiplying by a half and reducing. Okay? Now, the reason I want to do this problem, not only because of the absolute value in the original, but the way that most people are going to write these, and especially the way that I introduced the concept, is that to create this one, you just drop the absolute value bars and do what was there, right? To create this route over here on the right, we then flip the inequality and multiplied by negative. But this side here then is actually it's further to the right on the number line than what this side is. Meaning that if I graph, so let's think about this. We've got x is greater than or equal to 23/5. So greater than or equal to 23/5 would be this interval here, 23/5 to infinity, right? Would you guys agree that everything in there is equal to 23/5 or bigger? Okay. And then this one here, x is less than or equal to 22/5. Well, that should look like this. Negative infinity up to 22/5, including 22/5. And just because of the structure that we use, a lot of people are going to write those two intervals down, and they're absolutely, but then they're going to union them, and they're absolutely right that they're supposed to union them. But remember that added concept that our interval needs to mimic a number line. Meaning on a number line, your numbers to the left should be more negative than your numbers to the right, correct? As I move along that interval, 23/5 is further to the left than infinity, but is negative infinity further to the left than those?
Yes.
Yes. So that second interval is messed up. These things need to change spots. I need to go negative infinity up to 22/5, union 23/5 to infinity. Okay? If on a test or quiz, because I'm early on you'll find out that I'm lenient, and hopefully you saw some of that maybe in your quiz. If you wrote this on a test or quiz, I would just write "be careful." Okay? And I would award points to it. Okay? But if you continually do that, let's say I give a quiz on Friday, which I'm going to do, and then something like this shows up, and you do that, I'll write "be careful." Okay? You do that on the next quiz, I'm going to write "be careful." Okay? But on the third one, you have neglected my advice to be careful. Does that make sense? So there you're probably going to eventually start losing points. All right? Our number line, our interval has to mimic our number line. Okay? And I want to kind of ease you into like a more difficult grading. I think what you're going to find out, and it's a rude awakening, is that when you get to like a college math course, college science course, you're going to have people across the entire spectrum on the ways in which they grade things. Okay, I've had people that said, "Okay, I'm going to be very easy," that they're a very easy grader, and then you have people that, I mean, if you forget a minus sign, the whole problem's wrong. 10 points missed because you've got a minus sign. Okay, or you do all the work, but you don't provide an explanation in English with properties and theorems and stuff like that you use that support the work. You got the right answer, no points because there's no supporting evidence, okay, or logic. I'm going to ease you into that, Okay, I don't want to just start right off the bat and say you need to be kind of totally in line with everything, but eventually that's kind of what we want to develop into. Okay. Questions on that stuff? Have you guys gotten to those? I know that time it's not due till tomorrow, but have you guys gotten to those handful of questions? And if you did notice that on that assignment, I did add exercises because somebody was crying about it.
Are we getting more?
I gave you some more.
Are we getting more homework tonight?
No new homework tonight.
I don't know why you're yelling.
Okay, no more homework tonight. But we do need to start 2.1. Okay. The way that I want to structure class, and again, this is kind of easing you into a more formal college course. Usually in college courses, you have a test about every 5 to 6 weeks in a math class. Usually they break it up to a semester of 18 weeks or 16 weeks. They break it up into 2 to 3 tests. So you might be doing tests over 3 or 4 chapters or 4 or 5 chapters at a time in those courses. It's kind of how Rhodes is set up if you took it on campus at Rhodes. Okay, I'm going to do it a little bit differently. I'm going to do 2 tests. Okay, I think that's going to do 2 things. It's going to obviously make us kind of ease into that transition of having more information on tests down the road, but at the same time, it's going to save us time in regards to finishing the course. Like if we had a test on every single chapter, we would run out of days and we would not get to all the information. Does that make sense? Yes. Can we? Let me get to this, and then once we get done with this, I can get to you, or between classes, I can help you with it. But we have to be able to condense our chapters into 2 chapter unit tests, just for the sake of time, and again to kind of train ourselves into that bigger and bulkier type test. What you're gonna find out with this chapter, though, this chapter of redundancy, a little bit of old information, okay, but we're going to hopefully learn it a lot better than we currently understand it. You've been introduced to this stuff in Algebra 2, used a little bit in Algebra 1, but we need a really, really solid foundation about what a function is, different ways of representing a function, what a function tells us, how we interpret functions, because then everything else that we do beyond this section talks about a function. Okay? There's a couple, when we get to conic sections, some of our conic sections are not functions, but everything else beyond this, we're going to have the question or the statement, are we dealing with a function? Because if we are, it's going to get me down this kind of pathway and approach to dealing with the problem, or is it not a function, so it takes me down a different pathway? Does that kind of make sense? Okay. So that's where we're headed. Early on, we'll talk about our kind of most basic functions. We'll talk about linear functions. We'll talk about quadratic functions, which we've already dealt with a little bit. The projectile question is a quadratic function question. But then we'll start working with like cubic functions. We'll talk about quartic and quintic and stuff like that, and then applications of those things. So if I'm using a cubic function, maybe an application of that is I've got X amount of material of cardboard. What's the largest volume that I can make for a cardboard box out of that area? Okay, so and we'll maximize those things. You guys do optimization problems last year?
Nope.
You did questions where a farmer has so many feet of fencing. What's the largest area that he can enclose on fencing? You guys did that with a rectangular like pen or something like that. We'll do that, but then we'll work and broaden that with cubics and quartics and quintics and different relationships. On top of that, there are a lot of theorems in calculus that start off with, for a function, if this occurs, then you can do this, okay? So what we talk about here is kind of the backbone for being able to do a lot of our rules and properties inside calculus. Okay? A function, simply stated, is a rule that assigns to each element x in a set A. Remember, a set is just a collection of things, right? Okay? What we're usually going to think about is that our set A is the real number line. It's the x-axis, is the way we usually think about it. Okay? But it takes every x in set A and pairs it with exactly one element, which we call f of x, which we review as the function evaluated at x, or maybe you guys remember y, okay, in Algebra 2, in a set B. Okay? So set B is usually your y values, or your vertical axes. So that's the definition. Okay? And you've got several different ways that we can model that